This is video number 1 for section 11.3, the Pythagorean Theorem. So all semester long, we have had as our focus the study of functions. And in fact, really the whole course has been divided up into a study of different kinds of functions. We've done linear, exponential, quadratic, rational, and radical functions. Chapter 11, the ending of the course, has just a few examples of some important graphs that are not functions. So we're going to look at some non-functions to wrap up the course. And in section 11.3, the particular shape that we're going to look at is a circle. Clearly, a circle in the xy plane is not a function. It fails the vertical line test, right? But it is still an important graph. The goal, really, of this section is to figure out what would be the equation of a circle drawn in the xy plane. Well, of all places, our story today begins with the Pythagorean theorem. This is likely something you've seen before. This is a geometry topic. The Pythagorean theorem involves working with what are called right triangles, meaning a triangle that has a right angle in it, a 90-degree angle. And it turns out that for any right triangle, there is a special relationship between the three sides. These two sides here, the sides that touch the right angle, are often called the legs, and we generally use the letters A and B to represent the legs. And then the final side, the side that's opposite the right angle, is called the hypotenuse, and we generally use the letter C to stand for the hypotenuse. Well, the Pythagorean theorem says that no matter how big or small the right triangle, there is always a relationship between these three sides, and it goes like this. Essentially, if you square each leg, the length of each leg, and add those pieces together, you will always get the square of the hypotenuse. Again, a squared plus b squared always comes out to be c squared. How is the Pythagorean theorem used? Well, let me give you a couple of examples. Letter A, here's kind of the standard type of problem. We're given a right triangle. I can see the right angle there. Two of the sides are given. The measurements are given. 4 units for this leg here, 10 units for the hypotenuse. But this other leg, I don't know what it is, right? It says find x. I'm supposed to figure out the value of x. Well, as long as you know 2 of the 3 parts, you can just plug all the information right into the Pythagorean theorem and then solve for the missing part. It doesn't really matter which leg you call A and which one you call B. I'll just match the picture that I did up here. So plugging in, that would give me 4 squared plus x squared is equal to 10 squared. I just filled in my 4 and my x for the legs and 10 for the hypotenuse. And then I've ended up with a quadratic equation, right? It's got an x squared, so I just need to think about how to solve this. Even just at first glance, I'm thinking the square root method is going to be my best bet because there is only one x showing. So let's isolate the base and the power. Let's see, I need to subtract 16 from both sides. That gives me x squared equals 84, and then square root each side to rid myself of the squared. Normally, I put the plus or minus here. In this real-life context, having a negative side makes no sense, so I don't need to worry about that. And I end up with x equals the square root of 84. If I'm interested in the exact answer, then I do need to simplify this by doing the whole good, bad, radical thing. I think if you look at the perfect square list, 4 is on the perfect square list, and 4 does go into 84 21 times. So that means the final exact answer to this problem would be x equals 2 square root 21. Or if you were interested in a decimal approximation, then of course you would just type that into the calculator and round appropriately. I got about 9.2, which looks pretty reasonable and realistic from the picture. The hypotenuse will always be the longest side of the triangle. Note that to get the approximation, the calculator doesn't care whether you type in square root of 84 or the simplified version 2 square root of 21. You'll get the same thing either way. All right, let's go down to a little bit more interesting example, though. Take a look at letter B. We're now here in the xy plane. This, at first glance, might not appear to be related to what we've just done, but take a look closely. The directions say, here are 2 points that are marked, right? I've marked them with dots. I've drawn in the segment connecting them. And the directions are, figure out how long that is. Find D. In other words, what you're doing here is you're finding the distance between those 2 points, the direct distance between those 2 points. Well, that's not an easy thing to do. It's easy to find horizontal distances in the xy plane, and it's easy to find vertical distances, but diagonal distances, I don't really have any great way to do that directly. Well, so what I'm going to do is I'm going to take advantage of the Pythagorean theorem. Perhaps you've already pictured in your mind the fact that while I'm not sure this diagonal distance, if I wanted to start here and end here, and I could only travel horizontally and vertically, I would go over to the right some distance, and then I would go up some distance. Well, that rightward distance and that upward distance, those are distances I can calculate. Let's jot down the coordinates of these 2 points. Looks like 2, 1 for the first point and 6, 3 for the second point. I can figure out these distances, these red distances. I can do that either by counting, or I can just think, well, for the x one, I started at 2 and I ended at 6. That's a difference of 4 for that distance. For the y distance, the up and down distance, I started at 1 and I ended at 3. That's a difference or a distance of 2. Well, do you see that this is a right triangle? Since I went right and then up, I've created a 90-degree angle here. This is a right triangle. That means the Pythagorean theorem applies. This time I know both of the legs. The D is the hypotenuse of this triangle. So if I plug that information into my Pythagorean theorem, I get 4 squared plus 2 squared equals D squared. It's another quadratic equation. It's in some ways even simpler. The D squared is already sitting here by itself. On the left, let's see, I get 16 plus 4, which is 20. And then I just need to square root each side to eliminate the squared. Again, we're talking distance here. There's no plus or minus issue to worry about. Distances are always positive. And essentially I'm done, right? I get D, that distance I was interested in finding, is equal to the square root of 20. I just need to look for the instructions about whether an exact answer or an approximation is desired. In this case, there's no specific instructions. We can write down both. The exact answer, I would have to do the good, bad radical. This is an easy one, right? 4, once again, goes into 20. And so the final exact answer would be D equals 2 times the square root of 5. And then reach for the calculator to find the approximate answer. I get about 4.5. That's what we're saying is the distance between these 2 points. It looks reasonable from the picture. I mean, essentially what we're saying is if we picked this stick up and moved it over here, it would be about 4.5 units long, and that looks pretty reasonable from the picture that we've got. Learning the Pythagorean theorem is the first step toward developing the equation of a circle, as we will see in the videos to come.